Physicists and chemists like to make a point about the distinctions between heat and temperature, and it makes sense because they are two different things that are somewhat related. The first thing to realize is that heat is a type of energy, and so that means that it's measured in joules, and this energy can be converted into a lot of different forms. Temperature is a reflection of the kinetic energy of particles, and rather than being measured in joules, it's instead measured in degrees or in Kelvin. And this graph here helps to show the distinction between heat and temperature and how the two are related, which they often are. They are often related to each other, but not always, as you can see at points in this graph. So the formulas that you'll see for heat are going to be Q equals capital C delta T, Q equals M times lowercase c delta T, and Q equals mL. The capital C here is the heat capacity of an object. And so that's a measurement of how much heat is required to raise the temperature of a complete object by 1 degree Celsius or by 1 Kelvin. So it's for the entire object. Lowercase c is the specific heat of a material. So if you have a large block of lead, for example, the heat capacity is the amount of heat required to increase that entire block by 1 degree Celsius or by 1 Kelvin, whereas the specific heat is how much it takes to increase perhaps a gram of lead by a degree Celsius. So specific heat is a measurement of the material rather than of the entire object. The two are related by the fact that specific heat is equal to heat capacity divided by the mass of the object. And that is reflected here because basically you multiply M by specific heat, and that is essentially the same as the heat capacity of that object. So be aware of that distinction between heat capacity of a large object and specific heat of a material, which then you need to multiply by mass in order to figure out how much heat it takes to increase the temperature of that object. The third thing is latent heat, and latent heat is a representation of a phase change. Normally, when you're staying within a phase, the heat often goes toward increasing the temperature of that material. But when you're changing phases, for example, going from solid to liquid in the melting process, you have to break those lattice interactions in the solid and turn them into liquid interactions. And so some heat energy is required to break the lattice interactions in the solid and instead turn it into a liquid. So rather than that heat going toward increasing temperature, instead the heat goes toward breaking bonds. And that is when latent heat comes into play. And so you can see on this graph here, we list the y-axis as temperature and the x-axis as heat. And notice that when you're within a phase, for example, this is the solid phase, this is the liquid phase, and this is the gas phase here. Notice that within a phase, if you add heat, you're also going to see an increase in temperature. And that's true in any of these. One thing to be aware of is that the specific heat of a material may not be the exact same number when the material is a solid versus a liquid. And if that's the case, then that will be given to you on a problem. But notice that there are also times where the temperature doesn't increase as you add more heat. And that is because rather than that heat energy going toward a temperature increase, which is basically reflective of the change in kinetic energy of all those particles, rather than the heat energy going toward temperature, instead it's going toward breaking bonds. And that is when Q equals mL comes into play. That is the latent heat equation. And so what that means is that rather than putting the heat toward temperature, instead you put the heat toward breaking the lattice bonds that define solid or breaking the intermolecular forces that define the liquid. And by doing that, you're allowing the solid to escape into the liquid phase, or you're allowing a liquid to escape into the gas phase. And so if you understand that distinction, I think it becomes helpful then because you can see where heat is very related to temperature. For example, when you're within a phase, but also when it's not related to temperature. For example, when you're going through a phase change and the heat is energy that's being put toward other purposes, then temperature increases. And I think if you understand that, then you should be capable of distinguishing the two when they try to trick you with these in MCAT answers.